Hey class, this is Professor Coles going through what will be the last class for the semester, focused on hull design, and we'll do a powering computation during the in-class problem solving session. So this is just an overview of what is quite a complex problem. What I'd like to do is talk about the particulars, the key geometric parameters that sort of control the hull design process, and I'll give you some relationships between things like Froude number and Bloch coefficient, and describe how those sort of come to be. So the fundamental design problem includes a lot of aspects. You have the key particulars or key dimensions that we've been working with in the project and the class, the length, beam, and draft, as well as the Bloch coefficient. These are sort of the four fundamental parameters. From that, you have the displacement, which you can compute from those four. So the actual hull forms sort of a compromise resulting from the need to satisfy all these kind of requirements, and I'll just go briefly through these. Capacity deals with how much volume or how much you actually have to carry with you. So this is the gross, the tonnage you have to carry on top of your own displacement. This influences the volume requirements as well as the spatial distribution of that volume. And if you are, for example, a container ship, stability is a factor, both intact stability and damage stability, particularly in naval vessels. Constraints, you have often, for many classes, you have constraints such as draft. You have to enter a harbor. You have to be able to get up a river, enter a harbor, go through a lock system. You have beam constraints. For example, the well-known Panamax beam, and now there's a new Panamax after they enlarged the locks. You have Suez Canal beam constraints, and these deal with progressing through these locks. If you're dealing with racing boats, sailboats, or powerboats, often there are rules that are applied. They can be simple rules like a box rule, whereby your boat essentially is to fit in a box. It could be more complex rules that devise relationships and implicit trade-offs, for example, between length and sail area. In sailing is quite a common rule relationship. And of course, aesthetics. If you're working with a client, they might be looking for a certain look to the boat, and that can, for example, a traditional sailboat with long overhangs will drive the actual geometry of the boat. Functionality, think about ferries, be able to roll on and roll off, loading the cargo on the decks. Think about naval vessels, they have to get people on and off, if they're doing beach landings. Hydrodynamics aspects, we'll talk a bit about this, but service speed, so trying to devise what is the speed of transit and the optimal economics in terms of transit. Higher fuel costs might get offset by quicker delivery times. And seakeeping, so you have if you have people on board, for example, you have to be able to devise a ship that's safe and has a nice roll to it, essentially, nice seakeeping properties if you have people on board. Maneuverability, if you're doing evasion or if you're doing chase, for example, we think about these nearshore corvettes or small naval boats. Coast Guard boats have to be able to track and catch other vehicles. And then costs. Obviously, you have constraints due to how much you're going to spend on this particular project, both in terms of the construction and the long-term costs, usually related to, for example, fuel costs, as well as the cost of actually maintaining the vessel. These basic dimensions, we've been working with prismatic Bloch coefficient, the location of the center of buoyancy longitudinally, and your length, beam, and draft. These are the fundamental quantities. From these, we can derive these derived coefficients. For example, beam to length ratio, beam to draft ratio, and our length displacement ratio are derived coefficients from those fundamental quantities. We can divide hull form classes by wave making resistance. We've essentially spent our semester focused on everything to the left of this line right here. We used as a rule of thumb, and we'll continue using a rule of thumb, 0.4 as being what we refer to as, quote, hull speed. And in the absence of any kind of, in the absence of hull shapes that allow you to progress through this hull speed kind of wall, the resistance will continue to rise, and the fuel costs associated with that. And when I do the in-class problem, we'll see how quickly that rises as you approach point 4, which is unrealistic for the ship we'll be looking at, but just I want you to see how quickly it rises at that point. The reality is if you want to keep progressing in terms of, and this is written in terms of Froude number, then you have to have hull modifications that actually reduce the displacement of the hull. So semi-displacement or semi-planing forms use lift, hydrodynamic lift, to actually carry some of the displacement of the hull itself to reduce the overall drag and allow you to get through this hull speed kind of barrier. Beyond, and these are rough numbers, but beyond about a Froude number of 1, now you're talking about ships that are fully planing or essentially supported by this vertical lift coefficient, or maybe hydrofoils, fully lift supported so that the original displacement of the hull is now up in the air and you're not dealing with the normal resistance due to those components. Also capable of Froude number greater than 1 are multi-hulls. For example, catamarans or fast cats are able to do that because they divide the displacement up among a number of hulls, each of which are very narrow relative to their length, so they have low wave-making resistance. So that low beam to length ratio that multi-hulls can have and still have enough buoyancy to float the boat mean they have low wave-making resistance, but they still have stability because the hulls themselves provide a moment. So these are options if you want to go to these higher Froude numbers. Unfortunately, due to the COVID situation, I had to eliminate the last week, which kind of dealt with these a little bit in really a qualitative sense. So we've been focused on the real ship resistance problem over in this kind of zone here. But again, we're not dividing in terms of speed, we're dividing in terms of Froude number, what's going on in these sort of classes of boats. A key ratio is this length displacement ratio. In some formula you see it written L cubed over del instead of L over del to the 1/3 power. Sometimes this is referred to as the slenderness ratio. And if we think about for fixed displacement, just simply lengthening the boat by either reducing the beam or reducing the draft, and essentially we're reducing the cross section and lengthening the boat, and we'll think about what happens. As you make the boat longer, your wave resistance decreases, really for 2 reasons. One is if you're allowing the beam to decrease, this causes your boat to be more slender, and the wave generating decreases. Also, as you increase the length at a given speed, your Froude number is decreasing. So you really have these 2 effects that are going on, both which contribute to a reduction in the wave resistance by purely lengthening the hull at a fixed displacement. The friction increases, however, because what happens when you lengthen the hull at a fixed displacement, your surface area will go up. Now, the resistance is a little bit complicated because you have competing factors there. One is that the form factor of the boat, we've been calling little k, will decrease because the boat is more slender, but the skin sweated area will go up. So in the end, the skin friction will go up. You should see when you do your homework problem, you're actually going to be running this problem through Holtrop and Menon, just to see what happens if you take a hull that you start with in the problem 1 and start monkeying around with it by simply increasing the length, decreasing the length from the original length, to see what happens to the different components at a given speed and then at a different speed. And you'll see at higher speeds where wave resistance is important, that the length is really a very important factor, and having a longer boat really benefits you in terms of this wave resistance. We see this all the time, for example, in sailing events where longer boats essentially are able to operate at a higher speed, and in the handicapping systems, they handicap them strongly based on their length in order to have longer boats competing with shorter boats. There is an optimal L for minimum drag. This is what's known as a hydrodynamic optimum length. Just shown here, we have this total resistance as being the sum of the wave and the friction. The friction's going up because the wetted area is going up. The wave drag is going down because the boat's becoming more slender, and the effective Froude number, or the Froude number itself, is decreasing. So there is some length at which these combine to make an optimal total. This is similar to what you found in your hydrofoil project of competing resistance components, resulting in some optimal parameter. In this case, we're thinking about the length, so the optimal length. There is a second optimal length that deals with economics, because as you make the boat longer, you have you may be reducing the overall resistance, which reduces fuel costs, but longer boats are more expensive to manufacture. Longer boats are also more expensive, for example, to dock, because you pay dockage fees based on length. So think longer is more expensive, less resistance, at least at lower lengths. And this results in a similar kind of trade-off where you have capital costs, or you think about this as construction costs going up with length, fuel costs coming down with length, resulting in some optimum. And in generally speaking, this economic optimum length is smaller than, or shorter than, I should say, than the hydrodynamic optimum length, and becomes sort of the constraining factor. Location of the center of buoyancy. Holtrop and Mennen tries to sort of capture this, but it's a pretty complex effect, and it deals both with the bare hull resistance as well as the propulsive efficiency. So that's what makes it a bit more complicated. These are just sketches showing the bow and the stern. This is the water plane, the water line of the water plane of the hull, at least one half of the hull, where the dashed line is some kind of symmetrical hull fore and aft. In the left picture here, we have we've pushed some of that volume aft towards the stern. Essentially, this would move the location of the center of buoyancy aft on the boat. We're seeing this more and more, for example, in sailboats these days, but mostly to try to get more cabin space. You have, in this other diagram, moving the location of center of buoyancy forward. Now, this is an extreme picture, but just to show you what shape changes we're talking about. So generally speaking, when you move the center of buoyancy aft, it allows for sort of a sharper entry at the bow. So it reduces the wave making at the bow. But now we have a fuller stern, and the fuller we make the stern, the more we have this sort of separation-based resistance or viscous pressure resistance in the stern. So that will go up, the wave making will go down. So you have competing effects as you move the location of center buoyancy aft. And it also has adverse effects on the propulsion as you move it aft, because essentially making a larger wake area in which the propeller is living. And so by moving the center of buoyancy aft, you tend to bring in these wake effects, which affect single propeller or single screw boats more strongly than dual propeller boats. So that becomes a factor, as well as how many propellers you have. As you move the center of buoyancy forward, you increase the wave making resistance, but decrease the viscous pressure drag and decrease the propulsion effects. The result is that at high block coefficients, forward is better. And this is shown in this diagram here. We'll start with this solid line here, which pertains to single screw propulsions or single propeller boats. You can see here, this is forward optimal LCB and aft optimal LCB. And when you go to higher block coefficients, you're better off with a forward location of your longitudinal location of the center of buoyancy. At lower block coefficients, you're better off with an aft location. And you can see that the dual propeller boats shown here in this, where I'm squiggling with tracing with a squiggly line, have a higher tolerance, meaning they would prefer the center of buoyancy further aft. The optimal location of the center of buoyancy is further aft in that case. And that's because they're less affected by the adverse effects to the propulsion that come with moving the longitudinal location of the center of buoyancy aft. Section shape is a big one because you have a trade-off between stability and wave-making resistance. And the wave-making resistance scales strongly with the beam, and the stability scales strongly with the beam. Basically, it's a function of beam squared. So you have, if you can make your beam greater, your wave resistance goes up, but your stability goes up. And that's sort of a trade-off we talked about in an earlier homework, where we said, well, if increasing length to beam ratio is good for reducing resistance, we'll just keep doing it. But as you make the boat more slender, eventually you're going to make it unstable. And you may find that in your project, if the game is to play with length to beam ratio, you may notice that the moment arm will eventually go negative, which means you've just created an unstable boat. these are sections of the hull. Consider this, for example, the midship section. You have a V-shaped form here, which is obviously a radical-looking boat. A U-shaped form, which is closer to a boat form. Both of those have the same midship area. So if you make a boat using this midship section, they'd have the same volume. But in the V-shaped form, you have greater beams. You have greater stability. So these sectional shapes play a strong role in that in that trade-off, that fundamental trade-off. The prismatic coefficient, we've looked at this semester. Higher prismatic coefficient basically means that you're taking volume away from the sectional area. You're dropping down your sectional area coefficient and using that volume and moving it out towards the ends of the ship. So this would be a top view of a ship, and this would be a distribution, for example, of the waterline. And by pushing more area to the bow and stern, you end up with a larger prismatic coefficient. At low speeds, you're better off with, and Froude number is the best way to put it. At low Froude number, you're better off with finer ends in terms of prismatic coefficient. But what happens when wave making starts, and this is because viscous drag is prevailing, and you reduce separation by having a more streamlined vehicle. However, when you get to higher Froude number and the wave making becomes more important, then what happens when you go to a larger CP boat, shown here by the dashed line, and you can think of this just as in a cartoon effect. You have a bow, the bow wave is created somewhere aft of the bow, and the stern wave, you can think about our two-wave theory we looked at early in the semester. The stern wave is created, I have these backwards because x over L goes in this direction. So this is the bow, this is the stern, where x over L equals 1. So in the bow, you have some kind of positive wave that's made just slightly after the bow and a negative wave in the stern here, and it's the interaction between them, and really the distance between them, that establishes the wave resistance, as we talked about when we were looking at how Froude number comes into play with wave resistance. And what happens is even for a given length boat, by making it fuller at the ends, what it does is it tends to push where the bow wave is manufactured and where the stern wave is manufactured gets spread out. So you're increasing the effective length of the boat by using a larger prismatic coefficient, by separating the bow and stern wave further, meaning you can go to a higher Froude number before they're adversely interacting. And so at these high Froude numbers where wave drag is important, having fuller ends means that you actually have decreased wave making resistance. This chart just shows what's called the Taylor optimum prismatic coefficient, and shows you as you increase your Froude number how it results in a desire for an increased prismatic coefficient. And these relate to certain hull forms. Two more items I want to talk about. These relate to the project, so I mentioned these in the project setup video. The first is a bulbous bow. And so we see these on quite a few boats now, particularly boats that are often operating at a consistent speed. We think about even cruise ships, you think about container ships. They spend a good chunk of their life running at a single speed or a single Froude number. And you can use the bulbous bow to reduce the wave drag at those Froude numbers if they're designed correctly. And just in a simple sense, you can think of here, in the absence of the bulb, the original bow wave was this green line. But the bulb itself generates its own wave that's somewhat forward of the ship, and that would be the blue wave in this diagram. And the resulting interaction between them produces a suppressed bow wave that is also moved forward. So again, we're increasing the effective length of the ship without increasing the length overall of the ship, and reducing the wave drag. Now these are typically tuned for a certain speed or certain Froude number. Outside of that, they may be detrimental because now you've increased the surface area. Certainly at lower speeds, the wetted area is going to be up, which so likely means the increase in viscous resistance that comes from the bulbous bow will probably outweigh that of the decrease in wave making. So if you play around with this in your project, you might find that you can make your situation worse or better by moving that bulb up or down in the water column. That's the HB term, or making it larger essentially in cross section, and that's the transverse area of the bulb. Just an example, the DDG 51 case. So they have this thing here is actually a sonar dome. So this was already here on the ship when it was originally built. Oh, this is not working for me. Hang on. So this is sonar here, and then they added this piece here. This is the bulbous bow that they added on here. It is shown, it is below the water line here. And actually what you see traced on here are the actual water lines that are occurring in the tank. So in the tank here, they can add or subtract this bulbous bow, measure the wave resistance in the tank as a function of Froude number to see, or measure the resistance as a function of Froude number to see what benefits, at what speed you get benefits. And they're also tracing, you can see the water lines are actually getting engraved into the hull here, and they can actually transfer them to true water lines, which is pretty cool. So what they found here is that typical cruise speeds, they were getting fuel reductions of about 7%. At max speed, you still had a reduction of about 3%, not as much a reduction. And then you had these sort of cost benefits to the fleet over a lifetime. There was a positive cost benefit. I mean, you can see that in this case, they were retrofitting, and it resulted in a positive situation. Most ships now, they try to design them from the beginning with these bulbous bows. But they do add certainly to the cost, because if you consider how the sections of the hull vary as you move forward and aft, they're all quite similar, but once you get to the bulbous bow, it is a more complex form in the front of the boat. And the last element I just want to mention is transom sterns, because this is something that you might be considering in your project. And so the transom of a boat is sort of the flattish section on the aft end of the ship, is referred to the transom. When we say transom stern, we're saying is the transom itself is immersed into the water column. In this case, it's indicated by, you can see where the water line has been painted on the hull. So when this is sitting in the water, it's on dry dock here, but when it's sitting in the water, the part of the transom is immersed. A ship like this has a flat back where the name is, but in this loading condition here, at least shown here, it wouldn't be considered a transom stern. It's not clear if it was fully loaded whether it would or wouldn't. Where these transom sterns benefit, we see these mostly in ships that go to sort of higher Froude number, like these Navy ships that are capable of breaching 0.4. They're spending their days at above 0.25, say. Here you can see how what happens is, if I draw a side view of the hull here, driving along, hang on, our hull got squared off. A side view of the hull, at very low speeds, the water's passing under the boat. I'll just draw in the plane of the boat. So I'm gonna slice the boat like this with a knife in the XZ plane. And so the water moves under the hull at very low speeds and will bubble up in the back here and leave the stern. Once you get to higher speeds, it will break away, because essentially it's a sharp edge here, and the fluid will leave cleanly from this transom. And you can see it leaning, cleanly's not maybe the best word, but it's breaking away from the transom here, leaving this gap. And you can see the entire transom, including what is normally wetted when it's sitting at the dock, is now completely exposed to the air. So you can consider and say, well, this is almost as if I had a boat where it was, I could insert a piece of foam on the back here and extend it out, see how the weight comes back up. It's almost as if I had a boat that was this long, making this particular wave train. And so you're increasing the effective length of the boat by using these transom sterns. And so it can lead to a decrease in the wave resistance, because it's as if you had a longer boat without the increased viscous resistance that would come with that added length. But in the perspective of wave making, you've essentially added length. And so that can reduce the wave resistance and reduce the overall resistance. The other example, there's other reasons why you have transom sterns, particularly on military vessels, and because the main one being, it allows you to put a door here, and you can have vehicles traversing in and out of the door, and you see that on a number of military vehicles. That's how they launch smaller craft that can, say, go to the beach. The downside is really that now you're adding this new component of pressure drag. The best way to draw that is here. If I think about at low speeds here, I have think about drag only due to hydrostatic forces. So I have some hydrostatic force acting on the bow here, but the bow is immersed the same as the stern. And so think of this as like a dam. The fluid pressure acting here in here is roughly the same, the hydrostatic component. And so you have a balance of those hydrostatics. Once you have a water line that looks like this, it's higher in the front. You have hydrostatic pressure acting here, but in the stern, there's only air fighting it back. And so now essentially you have what was closer to what we consider a dam, where you have hydrostatic pressure on one side from water, fluid, and on the other side is air, the air pressure, which is much weaker than the fluid pressure. And so you have to, dams obviously you have to be structurally intact to hold back the force. In this case, that represents a drag force. And so this is the downside of the transom stern. And so you find with these transom sterns, typically speaking, that they're beneficial at some range of speeds, and other range of speeds they're not. And so that's why we don't find them on every single ship. But this is a nice picture of one right here. So that ends what I wanted to say about the hull design parameters. In class, we will work a problem using hull trip momentum. We're going to go through a full calculation of ship resistance. We're going to add some propulsion to it using what we've learned from the propulsion section. We'll match it with propulsion and make some computation of miles per gallon, and then look at what happens, or I should say how the resistance scales with speed, how the different resistance components scale with speed, to sort of draw on what we've covered throughout the semester.